So in this video, we're going to talk about something called the integral, which is the second part of calculus, and it's probably just as important because it has many applications in a variety of fields, particularly in science, engineering, economics, and finance. So the integral is quite an important concept that we need to know. So just to recap what a derivative is, we found that the derivative of function dy over dx can be represented as y prime of x, and it is basically the gradient along a particular point. So it is the gradient of the function at that point, or it represents a tangent line to that function. So that's the concept of the derivative, and it is a local concept. But in general, we want to find what happens if we're given the derivative of a function and we want to get back to the original function. So let's say we start with dy dx and we want to get back to the function that it originated from. So how can we do that? That's the main question that we need to answer, and this is a question that people ask themselves when they were talking about calculus and what all the fundamental principles behind it were. So to talk about the integral, we need to take into account one of two things. First of all, what is the derivative of a generic function like x to the power of n? Well, we know that if we differentiate this function with respect to x, what we're going to do is we're going to apply the chain rule, and this is going to mean that we're going to have n times x to the power of n minus 1. We multiply x, the function itself, by the power, and then we subtract 1 from the power. And that's going to give us the derivative of that function. So what happens if we start from here and we want to get back to xn? So we want to get back to x to the power of n. What do we need to do to this function? So we're allowed to multiply, divide, and add and subtract things. So, well, obviously we want to divide the whole thing by 1 over n. So if we divide the whole function by n, then that n cancels out and we're left with a 1, which is what we want to get to. And then what happens to the power? Well, we need to add 1 to the power because we need to get rid of that minus 1 so that we get to here. So what did we just do? Well, we just went back from this function to that function. And this is what the process of integration is all about. It's about reverting the process of differentiation to get back to the original function. Now, it could be anything. What happens if we start from here? Let's suppose that the derivative of some function is this, and we wanted to get back to the function that it came from. Well, we would apply the same thing. We would have to divide by n, right? So we would have to divide by n. And what else did we do to that? Well, we added 1 to the power, so that's plus 1. So is this correct? Well, let's see what happens if we differentiate this function. Do we get back to x to the power of n? Well, let's see. Oh, actually, that should be n plus 1. Yeah, that's an important, very important thing here, because we need to make sure that this actually differentiates back. So let's take the derivative of this. We're going to bring the power down, n plus 1, n plus 1. And we're going to subtract 1 from the power. So these two cancel out, and these two cancel out, and we're left with x to the power of n. So yes, in fact, this would be what we call the antiderivative of this function. But there is one very important element that we are missing here, because in doing this differentiation from this function to that function, there is nothing that tells us that there wasn't some constant next to it that led us to this derivative. Because remember, when you differentiate a constant, it could be 1, 2, 10, whatever it is, it becomes 0. So it makes sense that if we differentiate this whole function, we get back to x to the power of n. And in fact, for any number that we choose for that constant, we always get back to this derivative. So our argument for the antiderivative needs to be that for whatever function we find using this particular method, we need to add a constant to it, because that constant is going to be there no matter what. It could be 0, but it could be 1. So, or 2, or whatever number we choose for it. So it is important to include it because it is implicit here. If we differentiate, the constant becomes 0. So we need to make sure that if we are taking the antiderivative or the integral of this function, we need to add c to that. So what is this whole deal with integrals, and how do we represent them? Well, we're going to take a function, x to the power of n. The integral is represented by this elongated s times the differential dx. So the general formula for this type of function is going to be this, x to the power of n plus 1 over n plus 1 plus the constant c. That constant is very important, so whenever you integrate any function, you need to remember to include that constant. Now, integration is a very interesting process because it allows you to go back to the original function that whatever function you integrate came from. So we also have standard results such as, well, what is the integral of cosine of x with respect to x? Well, we know that what function differentiates into cosine of x? Sine of x plus c. Because if we differentiate this whole thing, the c goes to 0, so we're left with this. Now, the same thing can be said about other functions that we have dealt with in the past. So if we consider the integral of sine of x dx, what is that going to be equal to? Well, we know that cosine differentiates into sine, but cosine goes to minus sine. So in order to correct for that, we need to make cosine negative, because minus cosine would go back to sine. So this would be the integral of sine of x. And the same applies to other functions. So let's have, for example, e to the power of 3x times the differential operator. So what is going to be the antiderivative of this? Well, let's think about it this way. If we write e to the power 3x, because we know this shouldn't change, plus some constant, does this differentiate back into this? Well, let's have a look. e3x plus c is going to become 3 times e to the 3x. So obviously that's not what we have here. If we want to have that 3 in here, we're going to have this. We're going to have to put that 3 in there forcefully. But in order to do that, we need to manipulate this equation in such a way that we can actually allow for that 3 to exist within the integral. And the only way to do that is to have a reciprocal on the outside of the integral that is 1 over 3. So what happens with this? Well, this is the same as writing 1 times the integral, because this 3 and this 3 will cancel out. But now that we have this, we can actually integrate, because we know, well, this will be the integral of that. But now what we have here is a constant at the front, so we need to multiply whatever result we get by 1 over 3. And similarly, 1 over 3 will be multiplied by the constant, but because it is a constant, and a constant times a constant is another constant, we don't need to include the 1 over 3 here, so we can just leave it as it is now. So that's one of the things that we need to think about. When we get the function that we integrate, do we actually get back to the original function if we differentiate it? That's the easiest way you can check whether your answer is correct. And the integral has some very nice properties as well. Just like the differential operator, the integral operator, which would be represented by something like this, has the property of linearity. So linearity means that if you have an integral of a f of x plus b g of x, then this is equivalent to writing integral of a f of x dx plus integral of b g x dx. So it really doesn't matter. If you have a sum of functions, you can take the integrals of each of them and then add them together in the end. So that's a really nice property that the integral has. And because it is also a linear operator, we can it has that property. We can rewrite this as a f of x dx. So any constants inside the integral can actually be taken out of the integral like this. So this is the same as saying b times integral of g x dx. So that's what this would actually come to. And there are a lot of other properties that the integrals have, but for now this is what we need to do. So if we had, for example, just to show you what this would work, as we have, let's say we have the integral of some function cosine of x plus e to the 3x plus x to the 5 dx. What we can do here is we can essentially integrate each of these functions individually and then add them together. And because each of them will have their own constant, in the end what we need to do is group the constants into a single one. So we can just call it c again. So what is the integral of this? Well, that's going to be sine of x. The integral of this we just discussed is going to be 1 over 3 e to the 3x. And the integral of this is going to be what? Well, we have to add 1 to the power, x times to the power 6, and then we're going to divide by the new power, which is 6. So this is going to be that. And then we're going to add the constant c at the end. So this is going to be our integral. In the next videos, I'm going to show you more techniques about integration. But for now, just know that these are some of the essential elementary properties of integration. And this is something that will become very handy in the future videos when we talk about actual physical applications of the integral.